select rightly those different types of tumors. And the sparse PLS is going to tell you what are the genes that actually explain or differentiate your subtypes of tumors. So the first, the A plot here is going to be, it's a Pca plot. So this is an unsupervised analysis that you run on the data, and then you can color your dots according to the tumor subtype, and you can see whether that corresponds to what you were expecting or not. These are some, so at the bottom here, these are the parameters to choose, so I'm going to skip that for now. The second one is a PLSDA, so this, here you ask, now I want to discriminate my different subtypes, and you can have a look at your samples and see whether they color now according to the subtype. They should, because you asked the method to do it, unless your data are really bad. And the third plot here is the result of a sparse PLSDA. So the PLSDA that selects the genes that discriminate your classes. And so you will see in the outputs, I think there should be a list of genes then that are spit out by the method to tell you how good those genes are. I don't know if you're familiar with heat map, but that's a way also to visualize a large-ish data set. And this is a Roc curve, and the Roc tells you how good the method is at predicting. Okay, so those methods can predict. I haven't told you about this because it would take me more than 1 hour. But basically what you can do is you can have a training set where you train your model. You know, you learn, you tell the method, I want to discriminate those groups. I want you to identify the different genes that drive the differences. And once you have trained your model, you can test it on an external data set. So for example, you know, a new cohort that comes in, or some data that you've secured on the side that has never been touched by the method, you can then apply your trained model to your new data and ask, you know, what do you think? Do you think it's that tumor, or do you think it's that tumor? And because often you have the truth on this test set, then you can calculate how bad or good your model was. So we were discussing with Tasha, the problem of overfitting. Overfitting is when you train your model too much in the data, you stick to it, and it doesn't generalize to some external data set. So if you have access to an external data set, that's the best way, because then you can evaluate how much overfitting your model is doing, because sometimes we just stick too much. If you don't have access to an external data set, which happens very often in biology because everything is expensive there, what we do is we do cross-validation. So we subset the data artificially. So imagine each of you here are my samples. What I do is I say I'm going to divide the room into 7 tables. And I'm going to put 1 table on the side. So you guys, I'm going to train the model on you. And once I've trained, I have my signature, my genes, then I test it on you. And I see how good I am. I do that once, and then I do this again for the second table, and so on. And then I average the results. And that's the best unbiased way we can do to assess how much overfit there is. Okay, so it's just an artificial way of dividing your training set and your test set. So so the exercise or tutorial should be, so you have either a R&D file or a R file, so depending on, you also have the HTML file. So start with the PLSDA, and you can run it, depends how you like to work. You can take the R code and run it one by one. There's a bit of text that explains what's going on, and I just leave it to you for about 10 minutes. I can eat my pizza now. And if you if you have any bugs or questions, you can ask me. And there's also Solange and Eva, who are my students, and they also know how to use mixOmics. They can help you out too.
That's where it was there. I mean, you I looked at it. Yeah, and I looked at it before, like we were sitting here, and I looked at it. I tried to do it again because I did it yesterday. I sat down and I started. I was like, oh, I'm gonna see load it up. I like set up a clean thing and then loaded it up and I kept thinking about it like freaked out.
This is RGL, but it shouldn't put it on its own.
Oh yeah, mine. I don't know what that is.
But it should
Do you have
I know it's annoying, but you can try to type in, if you make this folder, then you have two windows.
Yeah, I know. Yeah.
your R session. Yeah, something installation should be the features as well.
Yeah, it is very.
The actual word. I think it's that you wanted to be super. I have that, but if you did the export, I'm just trying to solve it today. One different.
I just went to one.
Yeah, something on the website.
I haven't done anything.
Yeah.
Yeah, I think that's a problem.
Yeah, that's probably what it is.
Yeah. Yeah, it's if you have need the export.
I'm installing it now.
Yeah,
I think because I just updated, I used to have it, but I think I just updated my computer and it didn't transfer.
Okay, would you like me to go through the example or you want more time? I feel like a lot of people are bugged down from the start. I cannot install it. Sorry. I'll show you what you were supposed to do. So these are the data I show you. So this is if you do a principal component analysis. So you just have those, I put them blue dots just to show you that we don't know what those tumors are. But you can then, so this is a function plot indiv for plot individual. And so for any method you use, it's going to be called plot indiv. So we put a lot of effort in the different options that we wanted in those kind of plots. So you can actually choose, for example, to include the subtype, the tumor subtype information in the plot. So it's exactly the same plot. But you can also choose the legend. There's a few options here. And you can see that the samples or the individuals don't cluster according to the tumor subtype. So it means that the variation or the information in the data, is not necessarily linked to tumor subtype. So one way to then force the model to explain the tumor subtype is to do a supervised analysis with PLSDA. And so here you include the tumor subtype information. So here we have 4 subtypes. They call EWS, BL, NB, RMS, and we have the different breakdown of the different samples where they belong to. And then you run a PLSDA model where you input your X matrix plus your outcome Y and the number of components you want. Because I told you, you can choose a large number of components or only a few if you want to reduce the dimension of your data. And then you use plotting div again. So that's pretty easy. It's plotting div of your object. You may want to specify the components. So here I want to plot component 1 and 2. Actually, you don't even need to do this. There's a few things we try to simplify. You can put confidence ellipse plots around your groups, and you can see now how there's a good discrimination of your tumor subtypes. But it's just a PLSDA model, which means that it doesn't select the genes. Okay, so you just know that you can discriminate your different groups, but you don't know why, how. So following this, another thing you can do, and that's our latest addition, is it's the same plot as before, but you can visualize the prediction area. So each color here represents a group area. And so you can imagine that if you had a new test samples coming in, you need to project them onto that space so that they're called blue, orange, gray, or green. Okay, so that's the prediction part of it. So with the sparse PLSD, I'm just going to skip a few details. There's a sort of a tuning step to do to choose the optimal number of variables that you want to select, because the method is not going to tell you, it's 10 genes on the first component and 20 genes on the second component. It's like, it needs a bit of help. So we try to assess when is the best prediction or when does the method performs the best, depending on how many variables we select. So I skip the details, but it's actually on the website if you want to have a look at the functions you need to use. And at the end, you obtain, from this tuning, it tells you that you should select 9 genes on the first component, 280 on the second, 30 on the third component. And so you run your sparse PLSDA on those parameters. And then you do, again, a plotting div, and this is what you see. So you see the discrimination is not as clear as before because we removed a lot of variables, but we are confident that the variables we selected, for example, the 9 genes, are the ones that really drive the differences between the orange group and the other groups. Okay, so so this is the component 1 and 2, and you can see on the component 2 there's a few groups that overlap. But you can add another component in your model, and you can see how the discrimination starts to appear. So what happens is that the method tried to compress the data, and the first component was more about orange group versus the other groups. The second component tried also to discriminate the other groups, didn't succeed too much, but the third component helps you really to then discriminate all groups. And so there's other graphical outputs. So you can, this is the weight assigned to each gene. So here we have 9 genes that were selected. This is the most important gene at the bottom and so on. And the color represents how expressed or present that gene is for that specific group. So this is the orange group. So the first component selected a lot of genes that discriminated the orange class versus the other class. And then you can have a look at the second component, and you can see there's a lot of genes here. That a part of the genes discriminated the blue group versus the other group, and so on. So you can have a bit more insight into the genes that you select. So the third component is actually pretty clear. It's, it's green versus gray. And so there are some other outputs as well, but I think in the interest of time, I'm going to show you. So this is just to give you an example of when you have one data set, what do? You do a PCA, you have a look, and then if you have an outcome or a response and you want to predict and you want to select the key variables, then you do a PLSDA or a sparse PLSDA. The other example is for the N integration. So remember, we have multiple data sets. Here we have 3 data sets. So we have 150 individuals. They actually breast cancer tumors. And we have 3 data sets, 3 biological data sets. But you can imagine you're measuring anything that is, in 3 blocks, 3 different types of variables. So one is we call it the mRNA, macroRNA, and proteins. And we also have 3 tumor subtypes. So we know that among these 150 individuals, they divided into 3 breast cancer subtypes. And the method we use is called a block SPLSDA because we have multiple blocks of data. And you will see that the first plot is the sample plot, but you have 1 plot per data set. Because remember, we summarize each data set with a set of components. So we can then reuse those components and have a look at what's happening in each data set. So remember, we still integrate the common information from the data, but we can plot them separately. And you can see how the model was able, so these are your samples and the colors correspond to the different breast cancer subtypes. And you can see how the model was able to find common information from one data set to another data set, because you can see exactly the same trends. And then we are able then to identify the different types of variables that explain the different subtypes. And we have different variable plots to show or to understand how correlated they are, or, you know, do they explain the same thing, and so on. So what I can do is I can show you here. That's not what I wanted to show. This one. So here we have our 3 data sets. And then I input the breast cancer subtype information. So they're basal subtype, HER2 or luminal A. We have different parameters we set up. Let's just jump to the final model. So this is our final model here. So you run a sparse PLSDA, a block sparse PLSDA. You input your data. You input your outcome or your subtype information. You decide how many components you want and how many variables you want to select on each dataset and each component. And this is an example of the output of, you know, the gene selection we have. So here, this is a very small selection of 5 genes, but they seem to be enough to discriminate the different breast cancer subtype. I'll show you just the genes, but then you have the macroRNA and the proteins as well. So this is your, you know, overall selection of variables that you have. And this is the sample plot I was telling you about. So you can see how we extract. So this, for example, on that plot is only built on 5 genes. And that one, I can't remember how many macroRNA I had, maybe 10 or 15. And so it's built on 15 macroRNA. And this might be built on 20 proteins, but they all explain the same thing. And so when you have multiple data sets, this is what we mean by integrating. We try to find the common information from the different data sets, even though we measured those individuals at different levels or using different techniques. And these are the variable plots. So I'll show you one that we created, where so each of those variables on the side are the names of the variables we selected. And the link here represents a strong correlation between data sets. And that's for biologists is very interesting, because then we can understand a bit better what's going on in a biological system. So if you have a very correlated signature, we call it, then we think we have, you know, more information that we extracted from those data sets. And we also have, I didn't put it here, but we also have a network visualization also to visualize that. And if you, again, we have the different weights that are assigned to the different variables we select. And this is on the different blocks of data. So you can see how each variable contribute to which kind of breast cancer subtype, for example. And also, if you want to have a look at that, this is an example where we predict. So what we have in mixOmics is we also have a data set that we call a test data set that I've never used before. And what I do is I have my model that I learned before, and I say, okay, now you predict. So you use the function predict. You predict based on my model on this new test data. And then you can because you can calculate how often we have it wrong or right. Okay, so this is the truth. in the test data set, and this is the prediction. And so, for example, here it says that from all my basal subtypes, 20 were rightly classified as basal, 1 was classified as HER2, and 0 as luminal A. And so, and then on overall, it tells me that the method gets it wrong 6% of the time, which is not too bad for a data set like this. And that's because, you know, we selected the key variable, so we removed a lot of noise, and we did, you know, and because we build all the information from these different data sets to come up with a good predictive model. So some of the discussions I had with you, with some of you is, you know, is your method the best? Probably not. It's highly dependent on the data you have and the question you have. And so you will have to test different methods, different classifiers before you can make a conclusion. And even if one day it's that method that wins, maybe tomorrow you have another set of data and it's going to be another method. Okay, so try always to benchmark and test different data sets. Try to have a test data set if you can to evaluate the performance of your model. And if you don't, use cross-validation to create artificially those test data sets to make sure you're not overfitting and you don't, you know, give the wrong result. Okay. So I'm just going to finish off now. The other method that I haven't talked about, but it's very similar, is when you integrate independent studies this time and you want to identify the key variables that are consistent across independent study from different labs and different cohorts. Okay, so that's a very complicated problem too, because people use different protocols and they have different techniques and different technicians, and that creates a lot of variability in the data. So you can have a look at that example. Everything is on our website. And I wanted to finish with talking a little bit about, you know, our package development, because that's it seems like it's my main activity today, but actually no, I am a researcher, so this is just my side project. mixOmics started with only 1 or 2 methods. And the idea was that we were interested in integrating data, selecting variables, and visualizing. Visualizing was one of the key components for us in mixOmics. But after a few years, we had 17 methods that we implemented, and 12 actually our own. So we do actually develop our own methods. Like the methods I show you today are new methods that we created. And so when you start to create more and more methods, you need to stick to your vision and your philosophy, because you can't just, you know, match up, you know, a lot of different types of data that all focus on data integration. It has to have a theme, and our theme was visualization and using always the same type of visualization to help the users to make sense of the data. Then you can also have a look at, so once you create your package, you want to know how successful or how used it is for the community, because you don't want to do like some of the statisticians I know, which are, we're just going to put it on the CRAN because then, you know, the journal is going to be happy, it's open source and everybody's happy. You want your package to be used. You want your package to be generalizable to other types of data. So you can, in CRAN now, you can actually record the number of downloads per year. And so here, you know, we have quite an increase. You can also see where it's downloaded the most. So in the US, in France, of course, and now in Australia, but that took a while also for Australia to come. You can also track down where what is the version of the package that people download. For example, here, I'm pretty happy. So that was last year. I'm pretty happy because they seem to keep track, which means that my communication is okay. They follow us. But there's still, you know, a few people who are dragging behind like version 5, which doesn't work, full of bugs, you know. But so it's good to know where you are. Dissemination is via our website. So you can see, because we expanded so much, we had to organize it in different modules and it was a bit complicated, but we have all the tutorial on the website. But most of the dissemination I do through workshops. So this was a very quick example of a workshop, but we do run 2-3 days workshops by invitation. So people actually invite us to do those workshops, and we've done it mainly in France because we have a big user community. But there's going to be one in Melbourne, I hope, next year. And it's a full-on workshop because it can be, yeah. So we go through most of the methods in mixomics. And sometimes if we do a 3-day workshop, people can bring their own data to analyze it with us and get, our expertise and, get more hands-on. And that really helped to make mixomics well known because then people use it, they talk to their colleagues or their students who then use it, publish it, and so on. Branding is important when you have a big package. So, I paid for a logo. We had to choose the colors. It had to be colorblind friendly. And then I don't know if you noticed, but we always use the same colors, the same color scheme. And that's my branding because I know then people will remember it better with the logo and the colors. We also created flyers and goodies. So how does the R package work? It usually relies on the community. So we are a very small team. So we have 3 core, 1 developer, and a few contributors, but basically it feels like it's only one person job. But we have a lot of collaborators and advanced users, and they help us also. They give us a lot of feedback. They may detect a bug or something, and they tell us, and so we can fix it. I believe in open access and open community, which means that, the package is on CRAN before we even have published the method. The method is published in bioRxiv before it's even, accepted in a journal and so on. So everything is early release. And I do tell the people on the website, look, it hasn't been published yet, but we will welcome feedback. And by the time our method is published, then there's already adopters that are already using the method and they're ready to publish. So it's a really good way to push everything at once. We use Bitbucket for the management. We have different branches depending on the version we're working on. We get a lot of emails, usually between 5 and 10 emails every week where we give advice, consulting. They're often new users who have, critical questions about which method to use. And our main ambassadors are our collaborators, the people who attend the workshop, and some very early adopters too. And we also have, when you launched mixomics, you could see welcome, and if you have a bug, you can put it on the Bitbucket open issue. So it looks like this. You load mixomics, and there's a link. And if you click on the link, there's the issues that people reported. And so that makes it really transparent for us, because if people say, oh, there's a bug, then they have a look and they say, oh, it's actually been reported, so they're working on it. And so it helps us to manage the bugs and also be very transparent about it. And of course, this is not all unicorns and rainbows. So there are many cruxes when you develop an R package. And all main cruxes is that we've never had a mixomics publication ever. So people are totally confused on how to cite us. One of the other cruxes, is R. R is just difficult to learn for someone who doesn't know, and our main audience are biologists, and they don't know how to use R, so it's very difficult for them. The other difficulty is my team is a team of statisticians or computational biologists, and we're very thorough in the way we tune the parameters because we want everything to be perfect, and sometimes it doesn't work that way. Sometimes biologists want a straight answer. They want to know, I want to select 10 genes, and they don't want to go through all the tuning and things. So it's very difficult sometimes to give some advice without, having it too wrong from a statistical point of view, but also being usable for the users. And software development is extremely difficult to fund in Australia and elsewhere. And so that's why we're such a small team and we make such a small progress. It's because, we have to use our spare time basically to do it. One of the mistakes we've done is that we put it on CRAN instead of putting on Bioconductor, because at that time we wanted it to be widely usable to anyone and not necessarily only the biological community. But then history happened, and so we developed a lot of methods for biological data. And so now I think it would be a good time to convert to Bioconductor. And because we have about 150 functions, that's going to take us a lot of time. So we have to go from S3 functions to S4 functions. It's going to take us another year. And we're also working on different shiny web interfaces, so to help non-R programmers to use the package in a more easy way. and also for to run workshops for non-R specialists. So my tips would be that you need a good name. Okay, you don't do like all the statisticians who call their package SAA. Like what? Okay. You want a package to be either very small, that's very easy to manage, or gigantic. So this is our case. We're big now. And when you want to expand, you need to stick to your philosophy. Okay, don't say, oh, that method is cool, let's put it in there. Oh, and that method as well. Oh, but no, but they don't have any visualization, but that's okay, we still put it in. Okay, so stick to your philosophy. If you want to be strategic, you have to align your package development to your research or your activities or whatever you're doing. You will have to upgrade on managing skills and business development skills as well. You need to be user-oriented. Users come first, not us, the developers and the statisticians. In research, you know, we have a lot of transitions and people don't stay. And so you need to ensure the knowledge stays within the core team. So at the moment it's with me and I forget half of it always, but you know, that's really important when you have a big package like this, because sometimes I would talk to someone else, a developer from the team, and I say, you know, what could be good is to add that argument. And he say, well, I already did it, and it was in the last version. Oh, okay. Because yeah, there's so much to remember now, and you need to have a very either you're on your own and you're self-motivated, or you need to have a core that is supportive and motivated as well to push you. So this is my conclusion for today. I hope I could show you that multivariate methods in general are pretty flexible for different types of questions. You can explore, you can do some classification, integrate, and you can understand a bit better your data already, or sometimes go even more pointy and have, you know, identify key variables and suggest novel hypotheses and so on. But for me, the development of that package has been instrumental in my research, not only because it helps me as a researcher to sell my research, but also because there are many other researchers who are using the tool and they can make sense of their own data without my help. And this is the team that was based in Brisbane along the year who helped me with this. And we're also hiring 2 senior postdocs, so maybe I'll send you the tweet on your tweet. We have 2 positions that are also open in my team. And thank you for your attention. Oh, questions. So that's one question we had. So we can deal with repeated measurement. There's a method called multi-level. When you don't have many measurements, many repeated measurements, so, you know, 2 or 3. So what we do is well, you have to have a look, it's a bit complicated to explain here, but it's very basic. It's when you do a before-after, you know, cross-study design, these kind of things, where you don't have a lot of repeats. So we correct for the time effect. And we probably in the next 6 months, we're going to develop a method for time course data where you have more than 6 or 7 time points and you want to identify correlated patterns in your data across time. So yeah, it's coming. Yeah. So the components explain decreasing amount of information. Okay, so you need to include the first one. Then if you want to visualize your data, you need at least 2, because otherwise you can't. But after that, this is where it becomes complicated because there's so many combinations. So if you want to include 5 components, if you want to visualize it all, it's gonna, you know, it can be quite difficult. Some of the supervised methods we have, they tell you what is the optimal number of components that's going to make the method predictive, or, you know, the best prediction you can have. And after a while, the components don't add anything. It just adds noise. It doesn't add more information, so you don't need those. So yeah, so we do have some criteria for that to choose. But often, if it's just an exploratory analysis, people have a look at the first 2 or 3 components, and that's it. So the question is, how many samples do you need for integrating data?
No,
And yeah, how much? Yeah. So it's a very philosophical question when you integrate data, because some people think, well, I have different data sets and they measured on the same individual, so surely I have more statistical power because I explain, the same thing with different ways. But statistically, no, it doesn't hold up. So because the information is correlated, so we actually lose power. So that doesn't answer your question. So the more samples, the better. So what we do usually is, for the different data sets, we filter them. So, I show you examples with 2,000 variables per data set. We do 2,000 to 5,000 variables, not more, because I'm saying, look, there's not going to be 5,000 variables that are important in that data set. Depending on how many variables samples you have, I then advise either you do more exploratory analysis. You don't even look at the performance. You just say, this is how the data look like. This seems to be the variables that seem to drive, the information. But don't reach any conclusion if you have only 10 samples, because, it's very risky. If you have more, then yes, you can do, evaluate your performance and do this. But so usually, yes, if you have, the examples we give are probably, the right order of the samples we can deal with the variables. But it depends it mostly depends on your interpretation. I'm very happy for people to have 5 samples if they don't give me any p-value, they don't give me any classification error rate or any performance measure. And they just say, those seem to be correlated. That's what I think, but it has to be validated some way. Ooh. A bit. Yeah. You could use the MINT method. That's really the best framework for that. Is you have the same type of variables that are measured by different people and in different labs. And so the idea is you want to identify the common information across all those data sets while removing the variation due to the technical assistance and the fact that they use another reagent or another platform. Yeah, so this one tries to find the common information and remove some of the noise. The other option is to do a meta-analysis where you analyze each data set independently. You get some results and then you have a look at the overlap of your results from your independent data. But it can be underpowered because you don't have many samples per study. So that's the idea of this, the MINT is to actually bump the sample size, find a robust or a reproducible signature.